So this problem asks you to rank these different species in a solution of ammonium chloride, 0.20 molar ammonium chloride. And this is a really good exercise in translating the symbols and all of the chemical equations that we've been learning about to a small particle model of just what's in your flask. So it's good to have an understanding of what is in a mixture and in what relative concentrations, just to get a practical, I guess, connection between or to the chemical equations. So the first thing that I would say is, in any aqueous solution, the thing that you're going to have more than anything else is water. Once things get even slightly close to the concentration of water, they're going to be saturated and they're not going to dissolve anymore. So anything that's dissolved in water is going to be present in a much lower concentration than water. So I'm going to give water a 1. Whenever you see water in these aqueous solutions, you can assume that it's going to be in the highest concentration. The rest of this requires that we know what happens to NH4Cl when it dissolves in water. The first thing to notice is that it's an ionic compound. So this NH4 is a common polyatomic ion. It acts like a metal. It's positively charged. And this Cl is a halide. It's negatively charged. And so those two things are ions, and they form an ionic bond with each other, and therefore they will dissociate with each other when they're dissolved in water. And they may or may not undergo separate reactions with water. And so this is where you need to really understand how to analyze what salts do when they're dissolved in water in terms of reacting with water to form acidic or basic compounds. So the first thing that I'm going to do is I'm going to write down NH4+, which is going to be present in the water because of the dissociation of the NH4Cl. And I'm going to consider whether or not it reacts with water. And using our guidelines for recognizing common acids and bases, we can see that it's a nitrogen compound with a proton and with at least one proton and a plus charge. And so that's going to act as an acid. It's a weak acid, but it's going to act as an acid. And so we can write an acid hydrolysis equation for this, where the water takes one of the protons from the ammonium ion, and it leaves the ammonia, NH3, by itself, and then becomes the hydronium ion. Okay, so we can write that acid hydrolysis equation. And therefore, we know that some of this NH4+ is taken up by doing that reaction, and then some of this is produced. Okay. Before we go on with any more rankings, let's figure out what happens with Cl-. So Cl- plus water. Is this a reaction or not? And what I need to do is I need to recognize that Cl- is a group 7 anion. It is the conjugate base of a very strong acid, hydrochloric acid. And so the conjugate base of a strong acid is so weak that it's not even basic. So this is not going to participate in a base reaction with water. It's not going to pull off a hydrogen from water because it's too weakly basic. It won't do that at all. So I can write no reaction. Okay. So right off the bat, now I can determine that this chloride ion here is probably going to be in a higher concentration than this ammonium ion because none of the chloride is taken up from reacting with water, whereas some of the ammonium is. And this reaction here is has got a Ka, so almost all Kas are very small. This Ka, I think, is something like 5.6 times 10 to the minus 10th. So all Kas that we're really going to be looking at in class have negative exponents on them, which means that all of these weak acid-base reactions are going to be heavily favoring the reactants and not the products. So the NH3 and the H3O plus are going to be produced, but they're going to be produced to a much lesser extent than the NH4 plus. Okay, so already we can start ranking these. We can say of these three that I've underlined here, Cl minus is going to be in greater concentration than NH4 plus because none of the Cl minus is being used up in the reaction with water. And NH4 plus is going to be in greater concentration than NH3 and H3O plus because the Ka is so small. So NH4 plus is going to stay intact most of the time, and every once in a while it will generate an NH3 and an H3O plus. Okay, so we've already got some clues here. The other thing that we need to incorporate into our reasoning is the OH minus ion, and that's going to come from the autohydrolysis of water, autoionization of water, which is this reaction here. Okay, and we know that that's got a K of 1 times 10 to the negative 14th. So that's, this happens very rarely, but it does happen in water. And so you will get H3O plus ions and OH minus ions. How do those compare to the other things? Well, the OH minus ion here is going to be in much less concentration than the NH3 or the H3O plus here because that Ka from the ammonium is larger than the Kw from the autoionization of water. So even though both of these reactions will happen to only a small fraction of these molecules, you still will get more ammonia and more hydronium than you will get the OH minus. Okay? Plus, you have hydronium ending up in two places. You've got it here and here. So you're definitely going to have more H3O plus than OH minus, okay, because you've got it coming from two different reactions instead of just one. And then how does the hydronium compare to the NH3? Well, again, you get it two places. And so I would also say that that's going to be in larger concentration than the NH3. So this is kind of a logic problem here. Now we have like all these little bits and pieces of information that we have to put together. So now, taking this down here, we can say still that Cl minus is going to be in larger concentration than NH4 plus, which is going to be in larger concentration than the ammonia and the hydronium, but we know from down here that the hydronium is even larger than the NH3. Okay, so and because the Ka of the NH4 plus is larger than the Kw here of the autoionization of water, that means that we are going to get the ammonia concentration in a larger concentration than the OH minus. So less OH minus is going to be produced from the autoionization of water than ammonia is going to be produced by the hydrolysis of the ammonium ion. So let's count here. We've got 1, 2, 3, 4, 5. We've already done water. 1, 2, 3, 4, 5. I think we've got it. And so our final ranking is going to be the water is number 1. And then we've got the chloride ion number 2. Sorry, forgot the plus charge down here. The ammonium ion is number 3. The hydronium ion is number 4. The ammonia ion is number 5. And the OH minus, the hydroxide ion, is number 6. So you've got to put all these pieces together. You need to look up KAs when you have two reactions where you don't know which one is going to be going to the right